when it's not a network problem, identifying higher layer issues in packet data. My name's Wes Morgan, and I am basically what gets called a full stack troubleshooter these days. I started off as a Unix and Linux sysadmin, been doing open source for a long time. If you ever played NetHack or used GNU Plot, I wrote some code for those. I actually date back to the days of punch cards and paper tape. So I've been doing this for a while. About the last 22 years, I've been working as a software support and networking engineer. One of my passions is a cappella music. Another is emulation. If you've worked with SimH, Hercules, or the main project, big fans. My days with Wireshark actually go back to Ethereal release 0.4, which I ran on a ThinkPad 560Z with Red Hat Linux 5.2. So I've been playing with this for a while. If you're interested in social media, you can follow me on Twitter at WesMorgan1. Advance warning, you'll get everything from tech to networks to politics to music to insect pictures. It's a real stream of consciousness thing. So be forewarned. Why are we here today? Well, as I mentioned a moment ago, I've spent the last 2 decades in software support with an emphasis on networking, data centers, etc. It could be the network happens far too often when someone's looking at a software problem. And in my positions in the past, whenever anyone said it could be a network problem, it usually landed on my desk. But what I learned over the years was that it's only really a network problem 10 to 12% of the time. So, 1 out of every 8 things that lands on my desk actually turns out to be a network layer problem. But I've learned to see the clues to operating system issues and or application issues in packet data. And that can be a hard sell. When you go to someone and say, there's no evidence of a network layer problem, but we've got some indicators you do have a problem up at the operating system layer or the application layer, quite often you get pushback. So you really need to have your understanding complete and ready to explain when you present this information. So before you start, you've got to understand the environment. Right? Is this physical hardware, virtual machines? Is that storage local or remote? Are there intermediate devices in the way? Right? Because you've got to be able to walk through the data flow, where this piece of data is at every step along the way. And I'm assuming that you've already ruled out network layer concerns. Right? You've already made sure we don't have excessive retransmission, we don't have congestion or loss indicators in the data. You've got to understand the application in question, as well as the protocols it uses. And this is a step where Wireshark's dissectors can really help you. Because one of the big steps in troubleshooting that I try to teach is you always want to know what normal looks like. So if you're called upon to look at application performance from a network layer, well, you start by collecting data when everything's running fine. And you examine that data and learn what normal looks like. Then when you're examining production data or data during peak usage time, it's easier to identify the outliers. And when you do understand those problems, are they constant? Are they intermittent? Are they easily reproduced? Sometimes it's very simple. It's almost gift wrapped for you. We had a problem once. The customer said, this is really bad, but it only happens on the between noon and 2 p.m. on the last Tuesday of every month. Okay, that made it pretty easy. We could look at data from any other time and then compare it to that one known consistent problem time. You probably won't have that luxury. So we're going to talk about some basic steps. And the first one, if you aren't already using it, Tcp Time Delta. This is one of the most useful statistics generated by Wireshark. You might consider adding it as a column because it very simply means what's the elapsed time between this packet and the previous packet in the conversation. I spend a lot of time with TCP Time Delta, and we'll see that in some of the examples here in a moment. You want to identify request response patterns. And even if you're looking at encrypted traffic, you can often identify these patterns if you're correlating it with the application or operating system logs. So you can find 12.17.42 in my capture. I saw this. Well, 12.17.42 in the logs tells me this. So even with encrypted data, you can make some very basic timing analysis happen. So let's look at an example. This is a very straightforward, it's a small capture. I look at the TCP handshake and the subsequent acknowledgements, and they suggest a latency of about 43 milliseconds. Well, I already see my outlier, and it's right here with the red arrow, right? I gave this website a client hello, and it took 1,200 milliseconds basically to come back with a server hello. So that's the odd man out, right? I'm not too worried about 10 seconds before I sent a fin. I'm not worried about that. That is an outlier. Let's see if that happens anywhere else. So now I go back to the full capture and I say, okay, show me all the server hellos, right? And that's what my capture filter up there is. IP address equals ABCD and TLS.handshake.type equals 2. That's going to extract all the server hellos for me. Well, I look at the time deltas. There's a consistent 1,000 milliseconds or more just to process a client hello before coming back with the server hello. That's something you would definitely investigate, right? You're adding more than a second of overhead to every TLS transaction. That's something that's going to get rather bad rather quickly. And I will say that in preparing for this session, I went back and revisited this site, and whatever their issue was, they appeared to have solved it because they're now back to very, very fast response times between client hellos and server hellos. Another example, and this one again, we're looking at what appears to be a fairly short-lived conversation. But look at the dead air. We have 7 seconds where we're waiting on the server to give us the next chunk of data. Here's a 13-second gap, a 7-second gap, an 8-second gap. Okay, so we're looking in a conversation that took 46 seconds total. 35 seconds of that was dead air. And that doesn't make sense when we look at the packet lengths. There's not a lot of data being exchanged here. So there is something else going on here. Notice we don't see any retransmissions. We don't see any duplicate acts. We see no indications of congestion or packet loss. We just have a lot of dead air. And that's a situation where you almost always want to go back to those application folks and say, all right, what's going on with this get, right? If I hand you this get, what's going on behind the scenes, and why should there be 7-second delays, 13-second delays? And there's very rarely a good answer for that question. You have probably found a significant problem. So even without going into the specifics of a higher layer protocol, we've learned that a simple timing analysis can help us out. We can use the TCP handshake and teardown to get an idea of what the general latency is. We can use TCP Time Delta to identify outliers. We can look for dead air in what should be a fairly steady data flow. And again, that's a question to ask the application layer folks, right? Is your protocol something that should give me a steady data flow? I make a request, I get everything back in at once. If the answer is yes, well, then dead air definitely indicates a problem. And then looking for common factors across those outliers. Do we have a question? Okay, Jeff asked, so how would you read that? SSL shopper is waiting on Polo. All right, let's go back to that slide. So here's the 3-packet TCP handshake. We give the client hello. Polo offers SSLshopper.com the client hello. SSLshopper.com acknowledges that packet. And then there's 1.158 seconds before it comes back with its server hello. So that's the delta you're looking at, right? Because this acknowledgement after the client hello tells us the TCP stack on the other side is responsive, right? Polo sent its client hello. SSL shopper came back with an acknowledgement for that packet 47 milliseconds later. So the TCP stack on the other side is responsive, right? And the latency is within the same ballpark that the TCP handshake suggested, right? 43 milliseconds here, 47 milliseconds here. The TCP stack is consistent and it's responsive. And then all of a sudden, we're waiting a minute and 185 milliseconds. So that's how you need to read that. And you'll see that as a common thread in some of the later examples. Now, another case we find often is we got the response, but the client had already given up. And that's a situation, the hallmark symptom is obviously you see one side send a fin and the other side comes back with the response to the query later. You will sometimes see this happen across multiple conversations at the same time. And it can be a one shot, it can be an intermittent issue, depending on the transaction load. So what you have to do is understand the request that's being made and think about what the external dependencies might be, and then be ready to go follow them. So here's an example. And both the sequence and the timing are significant here, okay? So we see that the TCP handshake happens quickly. Client gives its request, this get right here. It's acknowledged within 2 milliseconds, right? Excuse me, within 200 milliseconds. 60 seconds of dead air. Rule number one, never trust round numbers. If you're looking at deltas and you're on a 30-second boundary or a 60-second boundary or a 180-second boundary, don't trust those round numbers. Okay, that's usually a very big clue that something untoward is going on here. In this case, it's 60 seconds. So the client effectively gives up. It's timed out. It sends a FIN. I'm done here. I can't wait for you anymore. Notice the server acknowledges the FIN immediately within a millisecond. Okay, so there's another indicator. The TCP stack is responsive. So this is not an issue with the operating system. We're not looking at that layer because the TCP stack is highly responsive. Well, 2 seconds after that, the server finally comes back with a 200 OK, but the client's already given up. So the server tries to send a FIN and the client comes back with a reset, right? Because it's already sent a FIN, it had already given up. So we've got a pretty obvious problem here. And again, there's no indication of extremely high latency. There's no indication of congestion or packet loss. So now we have to think about what's being requested. And we go look at the actual request. Get /RTC auth/verify.jsp. Well, that pretty much looks like an authentication URL. And it just so happens it is. And little investigation up at the application layer found that the server was consulting an Ldap server that had extremely slow response times. So the backend server was waiting on the Ldap server, but the client gave up first. Again, this is not a network layer issue, but this is the data that's going to drive you to find that problem, right? Because the logical question is, well, what would cause that much of a delay? You know, what would cause a 3-minute delay, excuse me, a full minute delay in an authentication request? Well, what do you have to do? We have to consult this. We have to consult an access control list or a directory. Okay, where's that directory? It's in another data center. Let's look at the response time between your server and the Ldap server. And there's your root cause. Another frequent issue here is what I call a request backlog. Oh, excuse me, do we have some questions? Nope, we're good. All right, so a request backlog. Again, consistent thread here, no packet loss, no congestion. We're looking for dead air in responses only. You may see additional requests. They may or may not be accepted. And then all of a sudden you see a flood of responses. So what does that look like? Here is Ldap traffic. And part of the Ldap protocol is that every search and its response share a numerical key. So this is request number 365. This is the result for number 361. This is the result for number 363. So all of a sudden, here at 12, 15, 23, 54, we stopped getting results. We're still making queries requests, and those requests are being acknowledged. But in this case, we go 7 seconds without a server response. Now, you might think 7 seconds, In those 7 seconds, 110 requests backlogged. And depending on the application, that could mean 110 application threads were held waiting, held semaphores, basically couldn't proceed until they got these results. So again, this might be a one-shot thing, and you look at it and you're like, okay, it happened once in 2 hours. We're comfortable saying that's a one-off. But if you look at your traffic and you find this as a pattern, that you're seeing 7-second or 10-second or 15-second backlogs throughout the day or throughout the period for which you've collected data, you're going to see application layer issues, because most applications today assume a certain response time. You know, they assume that they will not be held, seeing their threads held for 10 seconds every time they try to read an Ldap entry. But this is the sort of thing, and again, the common thread here, there are no network layer errors. This is all processing time and dead air. It's almost like we're looking for what isn't there. Which brings us to HTTP response time. Wireshark's computed HTTP.time is your friend. It can actually represent 2 different measurements depending on how you've configured Wireshark. Okay, you enable all the HTTP reassembly preferences, but then over in the TCP preferences, if you have the preference for allowing subdissectors to reassemble TCP streams turned off, then HTTP time will reflect the time to the first packet of the response, the one with the HTTP response code. If you turn that preference on, however, HTTP.time will represent the time to the last packet of the response. I will say normally that hasn't been a big difference for me. The one exception has been an application that dealt with consistently large payloads in HTTP responses and held its data in a remote disk farm. And in that particular situation, which if you think about it, is more and more prevalent with the rise of virtual machines, right? You have all the VMs on one machine and there's a SAN somewhere that's holding all their data. You can actually see cases where the delay occurs between the 200 OK and the actual beginning of data flow for the payload. So if you're in that type of an environment, that type of a deployment, you might want to compare the 2 values of HTTP time. We will not be doing that in this class, but that is something that's available to you if the deployment demands it. So again, we're talking about HTTP response time, and you've got to look at this in terms of the overall average response time. So we're going to look at not only the TCP handshake turnaround time, but we're also going to look at other requests, right? If there is a performance problem, are all requests affected or only some? If you see all different kinds of requests suffering from long delays, that may indicate a more general server stress situation. But if you only see delays in particular types of requests or even specific requests, now you're talking about problems on the back end. So you're going to need to understand, again, the application's data flow. If I'm asking for this, where is it? How does the server get it before it delivers it to me? We're going to follow the same general outline. We're going to look for outliers, And then we're going to look for common factors among them. So let's take a look at a few examples. So here's a very simple example. Again, a short-lived conversation. The client does a post, and it takes 29.95 seconds to get a response. Okay, what did I say rule number one was? Never trust round numbers. Well, that's close enough to 30 seconds. I think something's amiss. And sure enough, if we go down and look at the actual response, the IBM Traveler server is checking for changes in your server mail database. Okay, it should not take 30 seconds to check a remote database and see if you have mail. New mail, I should say. And again, this comes from knowing the application, knowing how it's configured, how it operates, right? IBM Traveler is now HCL Traveler, and it is a front end to Domino mail servers for mobile devices. So your Android or iOS phone talks to a Traveler server that then queries your home mail server to retrieve your mail. So knowing how the application operates, I can say with some confidence, yeah, it shouldn't take more than 30 seconds to reach out and check your mail file to see if you have new mail. So again, it's not a problem with the device. There's not a problem with the Traveler server. We need to look at the back end of the Traveler server talking to those home mail servers. All right, let's grab another example. This one's a little minor one. In this case, client connects, makes a post, 8 seconds response time. And nothing out of the ordinary there. You know, just processed your data. I offer this because this may or may not be a problem. This is the sort of thing where you'd say, okay, this is a short conversation. Yes, it has what appears to be a high response time. Is this normal? If you look at everything going on, if you get a data collection when there are no problems being reported, and you see that response times range between 6 and 7 seconds for this particular transaction, well, then you'd probably look at this and say, this isn't really an outlier, or it shouldn't be enough of an outlier to make a problem. Now, if you look at that data and you see that most of the time these get processed in a second, and then all of a sudden here's a time period where, oh, now it's taking 3, 4, 5, 7, 8 seconds, and then it goes back down to 1 or 2 seconds. That's when you're going to say, all right, let's go look at the logs. What else was going on at this particular time, right? Because the common factor among our outliers was they all occurred at the same period of time. Now let's actually drill through an outlier. I'm going to start. This is the setup I use, by the way, when I'm troubleshooting HTTP. And you can see I've got Delta as a column. I've also got the HTTP request, response, time, return code, and payload size. And a little set of buttons just for dealing with HTTP. So let's start by just looking at HTTP traffic. And now you can start seeing how my column setup works. Here's packet 188. It's a request. The response is in packet 189, so I can match that up very easily. 188, 189. There's the HTTP time. The return code was 200. There was no payload, which makes sense for an options statement. So I could scroll through this list and look for outliers. Oh, look, 319 seconds. Well, I think we're going to want to take a look at that. So that's a follow. Actually, before we do that, is this a one-shot? And so I have a button here, and it just uses the filter http.time is greater than 2. So show me anything with 2-second HTTP times or greater. Okay, so I have 3 here. They all took 319 seconds, which seems a little strange. So let's take a look at what we're dealing with. Okay, so here's a conversation. It has a GET, and that GET resolved in 4 milliseconds. We gave another GET, and this is the one that took 319 seconds. With next to no payload. And then we're done. So what you're actually going to do is go back and say to the applications people, okay, I have 2 of the same GETs to the same URIs with different data. Why should one take 4 milliseconds and one take 319 seconds? And it just so happens this is an antivirus scanning. And some things scan quickly, others do not. But again, we were able to, compare all our GETs, see what we have. We could say, show us everything with an HTTP time of greater than 2 seconds. And we were able to drill down fairly quickly and identify the common factor and the common variable. Common factor was calling the same remote processing, but with different data selections. Oh, I'm sorry, there was one other one I wanted to share. We've talked a lot about identifying problems on the back end. Well, let's take a look. Again, we're sorting through, and here's a couple of outliers. Here's 21 seconds, 44 seconds. Most things are sub 1 second, right? As I go through here, but I just keep getting some that look like outliers. So again, let's use a filter. Show me everything that took longer than 2 seconds. And what we're going to do here is pick some of these and start looking at the requests being made. Mm-hmm, 7756. And basically what you're going to find, in the interest of time, all the GETs to this particular family of URLs, the localnovos / anything, those were all our high delay URLs. So we went back to the applications people and said, why should what's different about these particular GETs? Oh, well, those are the pictures. Okay, what's special about those? Oh, those are maintained on a separate server. So they were actually using a database server to farm up all the images for their product catalog, and performance issues on that database server led to the pattern we saw here, where these particular URLs were leading to very high response times, right? Because if one thing on the page takes 15 seconds, then that's going to delay the whole page rendering. So this was very much in the user's face every time they saw these. Sometimes you're asked to track down a failure and it's not a failure. At least the two sides don't agree that it's a failure. ICAP is the Internet Content Adaptation Protocol. Most of your dirty word filters and digital loss prevention services, many of those are based around ICAP. Well, the application was reporting failing ICAP scans. Well, the packet analysis told us something different. Yes, they were failing, but the ICAP server was giving up before the application even finished sending its request. And the root cause turned out to be an undocumented request size limit on the ICAP server. So let's take a look at that, see what that looks like. So here's the ICAP query. That looks like a response. So let's just go ahead and take a look. So request, response, we're giving our data. The data is being acknowledged. Again, the TCP stack is healthy, right? It's acknowledging everything we're sending. And then all of a sudden it just comes back and says, oh, bad request. But as you can see, we're not done here, right? We still had more data to send. And then when we finally tried to finish sending it, we got a reset, right? The other side simply gave up on us. Well, that's one example. So let's take a look at another example. Let's see if it's consistent. So here's the next one. And the answer is yes. Here's the ICAP request. We get a 200 OK. And while we're giving it data, the server interrupts us and says, okay, bad request. We're not done. We keep trying. So this was the consistent pattern we identified, was that the server was simply not allowing the client to finish the request before rejecting it. And as I said, the root cause turned out to be an undocumented size limit in the ICAP server. We're going to take a quick look at a couple of fairly uncommon cases. One is you get through the TCP's handshake and nothing more. So basically, you're looking at your capture data, and this is what you see. Send, SYNAC, ACK, reset, over and over and over. Well, we know that the TCP stack handles the initial handshake. But when the handshake completes, that conversation is moved over into what's called a listener backlog queue. And every listening application has its own backlog queue. Well, if the application does not pick up the conversation from the listener backlog queue within a reasonable amount of time, TCP stack will kill it with an RST. If the backlog queue fills up completely, then any additional conversation attempts will get rejected with an RST, handshake RST. This is particularly likely if you're getting can't connect errors, but only during periods of heavy server load. The resolution to this problem, well, if you can do so, you can increase the backlog queue size at either the operating system or the application layer if the server can handle the additional load. And that's a very big if. Okay, you cannot just automatically say, well, the backlog queue is 120, let's double that. Well, that's just putting more people on hold, right? More people in the backlog queue. And if the application's not picking them up, they're just going to die off and you're not going to fix anything. So you've got to look for a deeper cause. You've got to look for that performance issue, and it may be a capacity issue. And you may have to go back and say, you need to resize your servers because this is why these drops are happening. Another point to keep in mind, you want to check every layer. Okay, this issue was presented as voice over IP's messed up, calls are failing. So everyone turned on debug, they started looking at the SIP stack, right? Well, here's the key factor, not just SIP, SIP-S, SIP over TLS. So when we did a packet capture, we never got to the SIP layer because the TLS handshake kept failing, right? We should have seen a server hello in response to the client hello. Instead, we got a close notify. So we were never getting through the TLS handshake to get to the SIP work to actually make a phone call. Root cause was an error in the server's TLS configuration. Okay, you might remember one of the things I said very early on was you always need to be prepared to look elsewhere. And that's what happened here. Everything came in focused on the SIP stack. Problem had nothing to do with SIP. It was all in TLS. We're going to spend our last bit of time together for TCP 0 windows. This is probably the most frequent indicator of system stress that I encounter among our customers. Simply put, a TCP 0 window indicates the TCP receive buffer is full. I have 0 room to accept any more packets. So don't send anything else until I tell you space is available. Well, the critical question is, why has the receive buffer filled? You may not find that out immediately. You may have to go dig. But rule of thumb, if you're looking at just a few short-lived instances, like it resolves itself within 10 or 20 milliseconds, that's probably just a hiccup. You look at them, double check them. Most of the time, those little short ones aren't a big deal. Where you have to worry is when you see lengthy instances, multiple instances on the same conversation, simultaneous instances across multiple conversations. Those almost always indicate some form of resource contention or threading issue going on up at the higher layers, up at the application layer. So we're going to start by looking at what I would call a cost of doing business example. We're in the middle of a conversation here. Yes, one side sends a 0 window and then updates it within a millisecond. Because you can see, here's a packet coming in, here's the recipient saying, okay, I'm going to acknowledge you, but I have my window's full. And then within 1 millisecond, it's sending a TCP window update to say, okay, I've got some space now. Okay, I've got more space. And then data resumes flow. And that all took place within three milliseconds from beginning to end. Also note, the window was recovered quickly within a millisecond. It went from a window of 0 to having a full 64K available, almost. Okay, so this is a hiccup. This is a one-off, unless we were to see tons of them happening within a short period of time. Okay, I'm sorry, I neglected to check for questions. When you say resize your server, do you mean CPU, memory, or storage? That's going to depend on the application that you're working with and it's going to depend on where you already sit with capacity. Usually, expanding memory is the first step, right? Because that's where all your conversations are living. That's where all your buffers are. That's where your backlog queue is. But if the problem is that the application is too busy with other existing threads to come pick up new connections, then you're probably looking at CPU resources. Okay, that's where you're going to have to go back to the application layer people and say, here's what the evidence says at the network layer. How we fix it, we're going to have to talk through, but I can tell you why this is happening. So the fix may lie somewhere between the operating system and the application in question. All right, so moving back, and I apologize for not getting to your question earlier. This is a hiccup. If I don't see a ton of these happening in the same data set, I call that a one-off. That's the cost of doing business. But let's look at a little more involved example. Okay, this one lasts a little longer. This one's about 6 seconds from, well, 4 seconds from beginning to end. Okay, 6 seconds, excuse me. Notice the recovery is slow. Window from 0, then it went to 5165 bytes, and then finally never did get back any higher. Notice too, we have an indication that the other side was actively waiting to send data. And that's because it was sending 0 window probes. Okay, it was actively saying, are you ready to take data now? Okay, because you notice in our previous example, it didn't last long enough. The other side never had to say anything. In this case, it is. And it had to check several times. Notice this is going to correspond to dead air as well, right? Because we're going from 2302 to 2308. We're going 6 seconds with nothing. So that's a little more significant, right? That's the sort of thing that's lasting long enough to create a real threading timing issue at the upper layer. Now, what about when the whole box is just getting slammed? Well, that's what you're seeing here. So we are looking at a 7 minute, roughly 7 minute period of time. I'm seeing 0 windows that are not only affecting multiple conversations, but also multiple protocols. And that's an important point, right? Because if all of these 0 window threads were port 80 conversations, then it would be like, okay, you got an issue with your web server, right? But they aren't. I've got conversations going on port 1516 and on port 80. And in both directions. Conversations this box initiated and conversations this box accepted from elsewhere. So I've got a bidirectional issue affecting multiple conversations across multiple protocols, all in roughly the same time. That is a definite indicator of a system-wide stress. Okay, that is, the box is choking for CPU cycles, more than likely. If it's multiple protocols, because if you think about it, multiple protocols being affected usually means multiple applications or multiple executables being affected at the same time. So it's not limited to any one thing. Okay, I'm going to take Eric's question a little later. Because I want to finish the thought on TCP0 windows. So with everything I just described, you've got a couple of different possibilities. You have to look at the situation from multiple angles. So in packet terms, that means you're going to look at the entire sequence. Wireshark will identify when a packet is going to fill the window on the other end. TCP window full. That is a Wireshark determination. TCP 0 window is straight out of the protocol. That's the other side saying, I do not have any more space in my buffer. 0 window probes, if they're present, probe acts, if they're present, until you see a TCP window update, which ends the 0 window condition because it's telling the other side, hey, I now have X bytes available. So when you look at these, you then have to turn around with the applications folks and say, what's an acceptable delay here, right? If this is going on and it's creating a consistent, 2-second delay, is that ruining your whole day? And they could well say, no, that's in our tolerance. It's okay if we get the occasional 2-second delay. If your answer is, well, what about a 14 or 15-second delay? They're probably not going to accept that. But again, you want to set those expectations. So let's take a look at an example and try to put it all together. So remember I said that you want to take a look at the whole picture. Well, with Wireshark, that means you're going to use tcp.analysis dot 0 window, 0 window probe, 0 window probe ACK, window full, window update, and fire it all up. And lo and behold, we have a chunk. So let's just look at this. We won't be using these detail views or the bytes view. So let's get as much as we can on the screen here. All right, these are all window updates. These are not a big deal, right? This happens anytime one side clears some space in its TCP receive buffer and there's not any inbound data at the moment. It'll just send a TCP window update. Hey, just so you know, you can now send this much data. So let's see where else we're going to go. These are all window updates. Aha. Let's get over to where we can see the time. So at 4:23:02, the server side, port 8081, threw a 0 window condition. 600 milliseconds later, we got a probe to which we responded, nope, still 0 window. Well, another 1.2 seconds went by before the next probe from the other side, and we said, no, I'm still 0 windowed. 2.4 seconds go by, right? And if you're counting here, we're already pushing 6 seconds of delay, of dead air. Okay, another finally 2.808 seconds after that, we finally got a window update. Now, was it sizable? Oops, excuse me. Not particularly. Window went from 0 to 5K. Okay, now it's going up to 54K. Okay, moving around, we're back to 64K. But that one incident, from here to here, gave us about 7 seconds of dead air. And then 7 seconds later, right, from 23:08 to 23:15, 7 seconds later, started again, another 0 window. 800 milliseconds later, there's a probe. 1.6 seconds later, there's another probe. 3.2 seconds later, 6.3 seconds later. In this case, we ate up 23 seconds. And then another 7. It's 30 seconds. 31 seconds. So now we're over 30 seconds of dead air. in 1 minute, plus the previous 6 seconds. So out of this minute, we haven't been able to exchange data for 37 seconds. That's going to create issues because there are application threads waiting on this data. Keep moving on down, and that's it. This is the sort of thing where I'm definitely going back to the application logs, and I'm saying, okay, 0423, show me the logs for 0420 through 0425. And that's an important point. Realize that when we're looking at these conditions, at the application layer, we may not see an indicator of this problem until after this time. Okay, so just because it was 30 seconds of dead air at 423.46, we might not see the entry in the log file of the application until 424 or 424 in 30 seconds. So whenever I'm doing log correlations, when I find an indicator at the network layer, I go to the logs and I look at a couple of minutes before and a couple of minutes after, just to account for the fact that by the time what I'm seeing at the packet layer bubbles up to the application layer, it could be another minute or two before we see the ultimate problem of this thread died, or this transaction was backed out, or this transaction failed. Now, we had a question, where would you start? Let's find that. So if you have a customer that has an intermittent slowdown when accessing sites, but by the time they contact you and you begin checking, the issue is magically resolved. I cannot tell you how many times that has happened to me. It is my least favorite thing in all the world. However, Wireshark equips you to handle that situation fairly well with the multiple capture files. So I would look at the application layer data and say, okay, we're looking at a problem with this protocol. And I'd say, okay, I don't care about payload at this point. So you only have to capture the first, pick a number, 128 bytes. But we're going to set up a rolling capture. And once we start it, your task will be to go stop it as soon as the problem occurs. So that when that happens, I have the problem, but I also have hopefully, 10 to 15 minutes before the problem. Because again, realize a lot of the issues that we're talking about build up over time. So when you see the application have a problem at 3:35, well, that could be the end point of a problem that started at 3:30 or 2:55, whenever, right? So with this intermittent problem that you're describing, that's exactly what I would do. I would say, first off, give me a good capture. And remember, I'm saying this from the point of view of the applications person, right? I would say I'd like to see an hour's worth of traffic when you're not having any problems at all, when everything's great, so that I know what normal looks like for your environment. Then we're going to set up this rolling capture so that we can capture everything until you have the problem and then take a look at it. And that's where we're looking at this option in Wireshark. I'm going to want 10 files. We're going to output them here, excuse me. So I could say 10 megabytes. We're going to call it like so. Use a ring buffer with, and I might do this and say, create a new file every 100 megabytes, use a ring buffer with 10 files. So that if you go turn this off as soon as the problem happens, I've got the previous gigabytes worth of traffic to examine. Okay, that's how I would start. And then after that, it's just going to be a process of elimination, right? And I'll tell you right now, that can be frustrating because I've had problems that, only occurred once or twice a week, and they weren't predictable in time or duration. So it was just, okay, here's the best we can do. We're going to set this up, leave it running, stop it as soon as you see the problem happening, and we'll go from there. And hopefully that will give us data to narrow it down a little further to be more precise with the next go round. None of the techniques I've talked about here are going to be a silver bullet. You will find yourself repeating these multiple times as you nail down a problem at higher layers. Okay. Well, that, as they say, is that. I very much appreciate you being here.